suppose so we need to go for a darker color. I have y equals x squared. So if I go ahead and my x and y, if x is 1, y is 1, x is 2, y is 4, x is 3, y is 9, x is 4, y is 16. So if I plotted that, not quite sure why I needed the grid because I'm not following it, but what the heck. So if this is my x and y axes, if I plotted 1, 1, 0, 0, plotted 1, 1, 2, 4, 3. I'm gonna separate that out some. So make that 1, 2, 3, and 4, and make this 5, 10, 15, 20. All right, so if I plotted the points, I'd have 1, 1, which would be a point 1, and then somewhere around there. 2, 4, 2, and 4. 3, 9, 4, 16, and 0, 0. So what would that graph look like?
A curve.
Okay, more specifically.
Gravel.
Yeah.
Probably.
So if I plotted y versus x, and the relationship is a quadratic, that's what I would get. Now, if I did x squared and y, again, same relationship, so x is 1, 2, 3, and 4. X squared is 1, 4, 9, 16. Y is equal to x squared, so 1, 4, 9, 16. If I plotted those points, make green will contrast. I'd have the point, well, 0, 0 still holds, 1, 1 still holds. 4, 4 holds. 9, so 4, 5, 6, 7, 8, 9. 9 holds. And well, the other one would be over here. What would that graph look like?
Line.
That's a line.
Yeah, that's a straight line. We'll pretend that's straight.
Today's straight line.
Yes.
So, now, if it comes time to doing an analysis over which is easier to analyze,
Line.
there are several people who have asked that question over the years, so now at least have it recorded. Or not, because I can't remember if I actually started it or
What
not.
was the question?
You are right. This was the one from the lab about why would we graph omega squared, not omega.
All right, there's another question about Master Set 7, problem 8. That was the orbit.
Yes.
So let's talk about work. Force times displacement. Or for you calculus fans. What is a dot product? There are two ways of multiplying vectors. One's a dot product, one's a cross product. What's the dot product do? Okay. So when is a dot product equal to 0? Let's back up for a second here. What is a dot product multiply?
Parallel.
So when is a dot product equal to 0?
When they're flat down
Parallel.
zero.
Wait, sorry, two voices at once? Wait,
I say when one of them is zero.
Oh. if one of them, yeah, I guess officially, yes, that wasn't the one I was thinking of, but yeah, that would work.
When they're not parallel. When one's not.
if it's like this, it would still have a non-zero answer.
When it's 90 degrees.
Yeah, when it's perpendicular. Perpendicular vectors give us a dot product of 0. So if the force being applied and the displacement, sort of an instantaneous displacement is, if they're perpendicular, no work is done. So if I have an object traveling in a circle, the displacement at that moment, the instantaneous displacement, is in the direction of velocity. So there's my planet, here's the sun. What's the direction of the force acting on the planet?
Towards the sun, towards the center.
So how much work is being done by this force of gravity?
0.
Yeah, because that's perpendicular. But if they're not perpendicular, the dot product is not 0. So if the angle between them is under 90 degrees, or from 0 up to 90 degrees, I'm gonna get a positive answer. In a sense, because the force is in the direction of movement, it's gonna help it along. If the force is between 90 and 180 degrees, I guess including 180, so if this angle is bigger than 90 degrees and less than or equal to 180 degrees, well, now the force is trying to oppose, part of the force is opposing the motion, and so you're gonna get negative work done. So this would cause an object to speed up if this is the force and the displacement. If that's the force and displacement, this would cause an object to slow down. In both cases, it would also cause change in direction. So if we're dealing with an elliptical orbit, it's a horrible ellipse, and there's the sun there. The direction of the instantaneous displacement is that way. What is the direction of the force?
Still towards the sun. Or
This.
towards the sun.
Towards the sun.
Towards the sun. That angle right there is less than 90 degrees. However, over here, well, let's put it here. My displacement is in that direction. My force is still towards the sun. And then when the planet is here, they're perpendicular, and when it's here, they're perpendicular. But, so it varies on an ellipse. In a circle, it doesn't. So that was the eccentricity less than 1, just meaning it's an ellipse. Okay, first off, was your question answered?
That part was, but I just was hoping we could go through what AU and all that.
Oh, that was just, the, AU is astronomical unit. That is the average distance from the Earth to the sun. Because astronomers, well, physicists in general start working in units that are more convenient to them. Instead of having to deal with something times 10 to the something, they just said, well, why don't we just make that Earth-sun distance 1 astronomical unit, 1 AU. Is that, because the question was asking about if it's in a circle, how much work is done during,
During one Earth year, what is the work done on planet F by the sun?
okay. So in that case, the Earth's traveling around the sun. The closer to the sun, the faster it's moving. So if we have planet X that is 40 astronomical units away,
Yes.
it's not moving as fast as the Earth is. So in one Earth year, this planet might go, that far. So if it's a circular orbit, it doesn't change because they're perpendicular the entire time. If it's an elliptical orbit, well, Earth goes around once, this travels, some segment of arc here. I feel like I still have not answered your question.
I'm just lost. I think I'm just asking like bad questions.
Is it you're getting thrown by, I throw in a new unit?
I mean, no, it's more like with the numbers, so it'd be 40 times further than the sun. Where would that come into play?
It doesn't. It's unnecessary information. If I were asking more specific information about how fast was it going, then it would come into play, but I think it's ultimately a conceptual question. Or I'm misremembering. So I just asked, well, the first one was, what is the work done? And the second one, you're given an answer of,
It says would the answer increase, decrease, stay the same, or it depends if the orbit were elliptical and, what's eccentricity?
yeah, eccentricity is less than 1. Just, again, it just means you've taken a circle and you've squished it a little bit. Other questions on this or anything else?
So as long as it's a perfect circle, the work done by either the planet or the sun will be 0 because it's perpendicular, or because it's,
Yep.
perpendicular.
And so the planet's going around the sun at the same speed, whereas in this situation, it picks up speed and then slows down, picks up speed, slows down. And as far as Earth is concerned, this is what we call winter, and this is summer. But our orbit's not that eccentric. Our orbit's much closer to a perfect circle than my drawing here. That's more like Pluto. At some point in the 90s, Pluto was the 8th planet in our solar system. And then it became 9th again, and then it stopped being a planet. And then it was a planet, and then it wasn't a planet. Who knows? It's a planet in here.
It's a dwarf planet.
Is it?
It's a dwarf planet.
Oh, I still,
Still be.
Still stands.
that's like saying, the Mets aren't really a baseball team.
That's true as well.
Well, what defines a planet as a planet?
What's that?
What defines a planet as a planet?
It has to be a certain size or shape. I forget what the
It has to have enough mass to be able to form into a perfect globe.
or close enough.
Yeah.
The powers that be. I was not asked to be on that committee, so I don't
Because
know.
Jupiter's just like a gas mass, but it's still technically a planet.
Yeah, it's. I think it's close enough to a sphere. Pluto's a little lopsided. I don't know. Or they just threw darts at a dartboard and
Yes
Jupiter
or no?
won. Pluto did not. All right. We last left off. Where I had ignored the weight of an object as it was oscillating. And the question is, what was my justification for ignoring its weight? So I have a spring sitting here, as a former colleague once said, fat, dumb, and happy. And then I add a mass to it. I know that if this is an equilibrium, and that's an equilibrium, well, actually, you tell me, what does equilibrium mean?
I know what it means, but I don't know how to define it.
Per-
Like I
perfectly
just
balanced.
kinda know.
Oh, that the, change in velocity is zero,
There's one.
that the acceleration is zero,
Yep, there's two.
and that the, change in force,
So close. Not change in force.
the force,
Yeah, total force.
total force?
Yeah.
Zero.
So, an answer of perfectly balanced is a little bit too vague. Well, not saying I haven't used that definition before, but it's vague in this context. All right, so this is an equilibrium. If I say static equilibrium, what does that mean?
Its velocity is zero.
Yes, and I missed what you said.
Velocity is zero.
Okay. And if I say dynamic equilibrium?
It has a constant velocity.
Right. And part of that, movement does not necessarily, a number of students do not associate that an object can be in equilibrium and still move, but movement's based upon the observer. So you might be in equilibrium, and if I start moving towards you, you now have a velocity relative to me, but that doesn't change your equilibrium status. All right, so at this point right here, I've got two forces acting on it. I have the weight, mg, acting down, and I have this spring force acting up. That's gonna be equal to the spring constant times how far it's stretched. So that distance right there would be delta x. We did that 2 days ago, you did that yesterday. So now, I'm gonna take that mass and I'm gonna pull it down and I'm gonna let go. So I pulled it down this far right here, so I've extended it, we'll just say a distance. Instead of putting a delta there, I'm just gonna make that x, and I'm gonna make this y. It is not in equilibrium. What are the forces acting on it? We did a force diagram of it.
Wait now.
All right.
Spring force?
Yeah.
Is that attached to it? What's at the top?
It's attached, it's the same spring right there, it's attached to something on the ceiling. I'm assuming that, I was really only care about the forces acting on the mass there. If we wanted to do the full force diagram, we would also include whatever's happening at the ceiling, but we'll ignore that. Force diagram, let's see. In which direction will it accelerate? I've taken the mass, I pulled it down, I let go. I hope so. It will accelerate upwards. Coordinate axes, what do you want to make the positive direction? One of those few times we were all here for when Luis said up to be positive. Decomposition, do we have to break either of them up?
No.
I hope not. Equation of motion. Plug it into F equals ma.
The spring force minus the weight is equal to ma.
All right. Substitution. Do I have an independent formula or equation for any of those letters?
For weight and for spring force?
Yes, for both. So I have kx plus y, because it is stretched. This was the original position right here, and it's been stretched x with just the mass on it, and then y with what I did to it. Minus mg equals MA. So now, I'm gonna distribute here, so I have Kx plus Ky minus Mg equals Ma. But I've already over here established that Kx is equal to Mg. It was in equilibrium at that spot. So Kx and Mg are equal to each other. And since I'm subtracting Mg, they're gonna cancel out. And so what I'm left with is just Ky is equal to Ma. What this means, if I look at the initial position of the spring before anything is attached to it, I need to include weight in my formula. If I look at this equilibrium position here, and I pull it down, I don't have to look at the initial, I don't have to care about X. So if this is equilibrium here with a mass on it, and then I pull that mass down, ultimately it just comes down to this, I can ignore the weight. But if I want to consider the spring stretched from its original position all the way down to here, then I have to include the weight. And there's a longer version of this where I look at energy, but it comes out to the same if you're looking at energy. And so 2 days ago when we were doing this, I ignored the weight when I did the formula, and this is the reason why. Questions to hear? All right. If I can describe the position, and I think yellow shows up better. X is equal to the amplitude cosine of omega.